Okay. So the next concept which we are studying is Ellingham diagram. Okay. See, previously we studied smelting process, no? Smelting process. Okay. So in this smelting process, what we have done, we have converted metal oxides into metals. This is what we have done, no? Okay. So metal oxide was converted into metal in the process of smelting. Okay, ma? So therefore, this is which phenomenon? This is reduction phenomenon, no? Reduction phenomenon. Clear, no, ma? So therefore, for reducing anything, we require a reducing agent also sometimes. Okay. So therefore, what Ellingham diagram says that it gives information. It gives information about suitable reducing agent. Okay. So what does Ellingham diagram give information for us, ma? It gives information about which is the suitable reducing agent for this particular reaction. Are you able to understand? For example, if I take some examples, let us write FeO, if it should disintegrate into Fe plus a half O2. Okay, ma? FeO can disintegrate into iron and half O2. For example, if it disintegrates like this, then for this one, delta G value is equals to plus 40, for example. Clear, no, ma? So what is the delta G value? Gibbs free energy, no? Change in Gibbs free energy. So for this condition, change in Gibbs free energy is plus 40. What do you understand by plus 40? Gibbs free energy already we have discussed many times in the previous chapters. So Gibbs free energy, if it is plus 40, what do you understand? What we understand is that this reaction is not possible. This is not a feasible reaction. Because reaction will be instantaneous, reaction will be feasible only when delta G value is negative. That is what we have studied previously. No? Clear, no? So therefore I say this reaction is not feasible. Okay? It cannot react by itself. That is the meaning of it. What is meant by instantaneous reaction? Already we studied, no? What is meant by instantaneous reaction? The reaction which happens by itself without applying any energy is called as instantaneous reaction. Clear, no? Water flowing from top surface to bottom surface, you need not spend energy. If I drop this pen falls down. All these are instantaneous actions which does not require any energy. And a reaction will be instantaneous only when delta G value is negative. Already we have studied, no? Clear, no? So therefore, let us make a note point of that also. So reaction is feasible. Reaction is feasible. In which condition, ma? Only when delta G value is negative. So change in Gibbs free energy, if it is negative, then only reaction will be feasible. Clear, no? And what is meant by delta G already we have studied, no? Delta G is equals to delta H minus T delta S. This is the equation, no? Okay, where delta H represents a change in enthalpy. Okay. And delta S value represents a change in entropy. This is what we have studied previously. No? Clear, no? Similarly, if I take one more reaction, for example, if I take carbon plus half O2, which converts into carbon monoxide, this is a reaction. Clear, no? So I see that for this reaction, delta G value is minus 100. So what do you mean by delta G is minus 100? This reaction is feasible. This is instantaneous reaction. So we say that this is a feasible reaction. Are you able to understand? Now what I try to do is, I will try to make out this relation by using carbon as my reducing agent. Okay? So here what is the reaction I am trying to get? I am trying to reduce iron oxide FeO into iron and oxygen. Are you able to understand? And this reaction is not feasible. So I will select a particular reducing agent such that which has the ability to reduce this oxide. And here delta G value is minus 100. No? Let us combine these two and see what is the reaction we will get. Okay. So FeO plus carbon, they can combine to become Fe plus CO. This is the reaction. Clear? No? Now here what is the total delta G value? For this one delta G value is plus 40 and for this one it is minus 100. So total value is delta G value is minus 60. So what do you understand by minus 60? We understand that this reaction is feasible. Are you able to understand? Ma? So why it is feasible? Because we got delta G value negative value, and the more the negative value, the more will be the reaction will be instantaneous, or we can say it is more a feasible reaction. Are you able to understand? So therefore, to reduce this FeO, carbon is behaving like a very good reducing agent. So Ellingham diagram gives about an idea about the reducing agent properties only. Which one behaves like a good reducing agent for which particular element? That information is obtained by Ellingham diagram. Are you able to understand? So did we make a note about that? So it gives information about suitable reducing agent. Is it clear? Make a note. Then we draw the diagram of it. See here. So this is the Ellingham diagram, a graph between. So on x-axis we are taking temperature, and on y-axis we are taking kilojoules per mole of oxygen. So don't be confused here. Kilojoules per mole of oxygen we are taking on y-axis. Clear? And on the x-axis we are taking temperature. Okay, ma? And these are the different reactions whose delta G values are measured here. What is this y-axis value, ma? This is a delta G. What is this one? This is a delta G. In terms of what? In terms of kilojoules per mole of oxygen. Are you able to understand? No. So for every reaction, for these many reactions, we have drawn the graphs here. Graphs of delta G versus temperature. So when you look at the graph, what do you understand? Sir, straight line lo madhyalo bending vachindi. What do you understand? Sima, slope of the graph is continuously increasing, no? For most of the graphs, slope is increasing. It means that as you increase the temperature, delta G value of these reactions will continuously increase. This is one observation which we see. Are you able to understand? Ma? So let us see what are the observations we see in this diagram, and based on these observations only you will get the questions. Clear? First observation is as temperature increases. Clear, no? Slope of each graph increases. Slope is not increasing, ma? Temperature is increasing. Slope of each graph is positive. That is better. Slope of each graph is positive. So slope of each graph is positive means what? It means that delta G value is becoming less negative. This is what is happening now. As temperature increases, slope slope is same. Slope of the graph is remaining same. But what is happening to the delta G value? Delta G value is continuously increasing. Increasing in the sense it is becoming less and less negative. Negative value is reducing. Okay. It means that feasibility of this reaction, what it is happening, feasibility of the reaction is reducing with respect to temperature. That is the meaning of this one, no? If delta G value is maximum negative, then reaction is more feasible. This is what we have studied, no? But as temperature is increasing, what is happening to delta G value? Delta G value is becoming less and less negative. Are you able to understand? So here what is the delta G value? Here it is 600. But here it is approximately some 450 or that. Are you able to understand? So delta G value is becoming less negative. So therefore what I say, feasibility of reaction reduces. With what? With respect to temperature. So this is one more point which I can see, no? Clear, no? And in some of the reactions you can see suddenly there is a change of slope. Suddenly there is a change of slope. So sudden change of slope indicates that state of this particular reaction is changing. It is converting from liquid state to gaseous state. Are you able to understand? So that is one more observation which we see. So therefore, when slope changes suddenly, then vapor state of reaction is obtained. Okay, ma? It means when slope is changing, we can see that it is converting into vapor phase. This is one more observation which we can see. Any other observation, ma? We see that for some reactions, delta G value is very, very, very hugely negative. And for some values, it is lightly negative. So can you say which one will behave like a very good reducing agent, ma? Ikkada manchi reducing agent edi. So that element which has highest negative value of delta G, that is a very good reducing agent. That's what we have studied, no? So out of all of them, which is a very good reducing agent? Magnesium is a wonderful reducing agent. Are you able to understand, no? So therefore, the more negative the delta G is, the element is a very good reducing agent. Okay, ma? Very good reducing agent. Are you able to understand? So here, who is a very good reducing agent, ma? According to this diagram, magnesium is a very good reducing agent. Magnesium is a very good reducing agent. Okay? Why? Because its delta G value is highest negative when compared to any one of them. So it is a very good reducing agent. And one more point which I can see is, Sima here, magnesium can reduce aluminium. Magnesium can reduce aluminium, that is oxide of aluminium. But aluminium cannot reduce magnesium. This is one more point which we can say, no? Are you able to understand? Why? Because for Mg, delta G value is more negative when compared to delta G value of aluminium. Is it clear? So therefore, magnesium can reduce aluminium. Aluminium cannot reduce magnesium. So write that point also. Completed, ma? So therefore, what we write? We write that magnesium can reduce aluminium, but aluminium cannot reduce. So this question was asked, I think, last before year, ma. So questions will be asked from these points only, ma, which I am writing on the board itself. Clear? So magnesium can reduce aluminium, but aluminium cannot reduce magnesium. What is the reason? Already we know, no? And one more point which I can write is, the element at the bottom of graph, can reduce element at the top until graphs do not cross each other. Graphs do not cross each other. Are you able to understand, ma? So when graphs cross each other, then the same is not correct always. See, for example, here, if I take the same example of magnesium and aluminium, magnesium can reduce aluminium only up to this particular temperature only. Are you able to understand? Beyond that, it cannot reduce. What is the reason? Because here graphs, they are crossing with each other, no? Are you able to understand, ma? So magnesium will behave like a reducing agent for the case of aluminium only until the graphs do not cross with each other. Only before this temperature only it acts as a reducing agent. Clear, no? So this much information I can get from this Ellingham diagram. So basically what does it say? It says that, so the more negative the delta G value is, the more better is the reducing agent. And the elements which are present at the bottom, they are very good reducing agent for the above elements. But above elements cannot reduce the bottom elements. These points we should understand. Clear? Now let us see what are the limitations of this Ellingham diagram. What we cannot understand by this Ellingham diagram. So that question was also asked previously. Okay? So limitations of Ellingham diagram. Okay. So first limitation is it says about feasibility of reaction, but not about chemical kinetics. Okay, ma? So it just says whether the reaction is possible or not, whether it is instantaneous or not. But it cannot say anything about chemical kinetics of the reaction. Clear now? Similarly, it cannot say anything about rate of reaction. Okay, ma? So how fast the reaction can happen, that information also we cannot get with the help of Ellingham diagram. Are you able to understand, ma? So these are some of the applications and some of the limitations of Ellingham diagram. And from this discussion only you should get the bits. Okay, ma? That's it. Okay. So next we are studying Hall's process now. Do you remember this process, ma, where we have discussed this one? We have discussed this one in leaching of aluminium. Clear, na, ma? In the concentration process of aluminium we have studied this one, Hall's process. So already we studied that bauxite, we have two types of bauxite, na, ma, ore of bauxite. One is red bauxite and the other one is white bauxite. So red bauxite can be leached or it can be concentrated by two methods. One is Bayer's process and the second one is Hall's process. So, and in red bauxite, which is the impurity? Fe2O3 is the impurity in red bauxite. And here Na2CO3 is the leaching agent. So these bits are very important. Okay. Which is the leaching agent in Hall's process, ma? Na2CO3 is the leaching agent. Leaching agent means what? Solvent, which dissolves the metal, is called as leaching agent. Okay. Already we studied, Nama, here the melting, what is meant by leaching process? The melting point of metal is less than melting point of impurity. In this condition only we use the leaching process. Clear, no? So therefore, and which is the solvent used here? Solvent used is Na2CO3. So therefore, let us see what is the reaction which happens, ma? So Al2O3 2H2O, which is also called as bauxite, it reacts with Na2CO3 to form so NaAlO2. Okay, ma? This is the compound which will be formed, and this is also a complex compound. Clear, no? And this is also called as sodium meta-aluminate. Sodium meta-aluminate. Are you able to understand? And this process we can call it as dissolution process. So in Bayer's process also we have studied this dissolution process. Here also we have one step which is called as dissolution process. Clear? Then what we do is we do the second process which is called as hydrolysis. Okay, ma? So in Hall's process, what is the name of second process? Second process is hydrolysis. Here what we do, we take this NaAlO2, sodium meta-aluminate, and we made it to react with carbon dioxide and water. Okay, ma? Then we see that what is the compound I will get? I will get again Al2O3 plus Na2CO3. These are the compounds which we will get. Are you able to understand, ma? And this Al2O3 upon calcination, not Al2O3, ma. So AlOH taken thrice, aluminum hydroxide. This is the reactant which we will get. And this aluminum hydroxide upon calcination, okay, ma? Again it will give Al2O3 plus H2. Okay. So this is the total reactions which are happening in Hall's process. Understood, Nama? Clear? And in this meanwhile, how we remove this impurity which is present? Impurity can be removed like this. Fe2O3 plus SiO2, they react to form FeSiO3. The same step we have studied in Bayer's process also. Clear, Nama? This is impurity. This is flux. And this is called as slag. Clear now? What is meant by flux already we have studied now. This flux, it goes and attaches with the impurity, and combinedly they will come out as slag, the final impurity. So this process we can call it as Hall's process. Okay? See, ma'am. So the last process which we are studying is Hall-Heroult process, ma'am. Okay? See. So what is this Hall-Heroult process? This is used for reduction of aluminium from its ore, ma'am. Ore. So already we have studied 3 methods, no? Concentration, reduction, refining. So after concentration, what we will get? After concentration also, Namaskaram. So after concentration, we get ore, no ma? Ore. So ore of aluminium we will get. And what is the ore of aluminium? Al2O3, 2H2O is the ore of aluminium, no ma? Bauxite. So after doing all these processes, Bayer's process, Hall's process, Serpek's process, we will get Al2O3 only. Clear, no? So that Al2O3 is refined, is reduced to aluminium by using this process called as Hall-Heroult process. So here what we are using 3 graphite rods. 3 graphite rods which are connected to same terminal, positive terminal. So therefore it is called as anode. Clear, no? And this container itself, it behaves like a cathode. It means the positive terminal of the battery we connect to these 3 rods. Negative terminal of the battery is connected to the container itself. Okay? And to this container there is an inner layer of graphite which is connected. So here you are seeing this red color layer, that is a layer of graphite which behaves like a cathode. Okay? And these graphite rods, they are present in what? They are present in this solution. Alumina, Al2O3, Cryolite and CaF2. Are you able to understand? Then immediately when I start doing this process, I see that aluminium continuously melts and it comes out of this vent. Vent means hole. Okay, ma? Aluminium comes out of here and here aluminium is collected. Okay? And let us see what is the process which happens here. So here I can write Al2O3 under Cryolite and CaF2 is reduced into aluminum. That's all. This is the process of reduction. Okay, ma? And here questions can be asked on the function of Cryolite and CaF2. Ma. Questions will be asked on this one. So let us write what is the function of Cryolite and CaF2. Okay? So what is meant by Cryolite already we have studied, no ma? What is the molecular formula of this one? Na3Al-F6. This is the molecular formula of Cryolite. Clear, no? So what is the function? Function is that they reduce the melting point of solution. Or you can call it as Al2O3. Okay, ma? So what is the first function of this Cryolite and CaF2? They will reduce the melting point. Melting point of the solution is reduced. Second function is they increase the electrical conductivity of solution. Okay, ma? So these are the 2 functions of this Cryolite and CaF2. Okay, ma? So this completes our topic called metallurgy.